going to get a little technical. Not too much, but I don't know if you guys have seen code today yet. Anybody seen code up here? All right, well, you're in for a treat then. Okay, so, and as I said, you know, I think that monitor's on back there, but feel free to come on up. All right, so we all have Christmas shopping to do, so let's get started. I was supposed to speak at 4. Good thing I got here early. Thank you, Doug. All right, so we're going to talk about stream processing, and in particular, real-time stream processing. And so, first question is, what is real-time stream processing? So you can. So who is familiar with? Okay, so Spotify music service. Raise your hand if you've either used iTunes, Spotify, or Pandora in the last year. Okay, that was a check to see if you're listening. All right, so if you're talking about real-time streaming, that's what most people think of is music streaming, right? So, or you know, some kind of video streaming. So most people know what streaming is, and these tools are used to do this kind of stuff. But stream processing is more about looking at each and every event that occurs. Yep.
Can you put the mic
Closer. Okay.
Yeah.
Advice from another speaker. Thank you. I won't have to yell as much. Okay. I don't know if that's better or worse. Okay. Is that better? Okay. Thanks, I guess. So traditionally, like when people put charts up, like what we're going to talk about, and then what are companies dealing with? And I know this is a conference focused on IoT, right? So Internet of Things. Sometimes it's also called Internet of Anything. Or everything. Pick a word, you know. So as you know, we live in a more connected environment. Our cars are becoming connected, etc. You've been listening to people telling me that all day, probably. So where does stream processing fit into that? This is the guts of how it happens. So we're talking about complex event processing, or even simple event processing. Not everything has to be complicated, right? I'm going to show you the tools that are used currently right now. So now I'll go ahead and introduce myself. I'm Paul Hargis. I work for Hortonworks. I'm a solutions engineer there. And so Hortonworks has a Hadoop distribution called HDP, Hortonworks Data Platform. So some of these slides are from Hortonworks, some of them are my own. But let's talk about new types of data. All right, so you guys have been talking about this today. There's the rate that data is growing is astronomical. There's new data available from sensors. So you guys were talking about that a little bit ago in the panel discussion. Everything is a smart device now, right? So there's a lot of data, and we also heard from some people saying, you know, we're now generating that data, but we may not be getting the most usefulness out of that data yet. We're still building the systems to do that. Luckily, the tools are now available. So these are just some of the types of data that, including clickstream data. So what we're really doing is shifting from, and this reactive to proactive is one way, but another way to think of it is, how many of you have jobs? All right, so most of you have jobs. Again, just check to see if you're listening. If this thing's on. Is this thing on? All right, so how many people run batch processes at their jobs? I mean, not you personally, but like your company runs those. Okay, so I'm going to make a prediction. I'm going out on a limb. In 10 years from now, nobody will be running batch processing. What they'll be doing is they will be streaming data into systems which can handle real-time data, and they will be doing it in a streaming fashion. So the tools that we're talking about are currently being used for real-time streaming, but that's not their only purpose, not their only utilization. I'm about to make some T-shirts called "Batch is so outdated. Use real-time, and so the question is, use real-time streaming. Why wait? So I will liken it to if you go back to 1990. when websites and internet started. So who would have thought at that time that print material, print newspapers would go out of business for the most part in about 10, 15 years. Those papers are struggling. And why is that? What is when they throw that paper on your front door? What has happened over the last 24 hours? Okay, I'm making a corollary. That is batch processing. Because what happened was, Dallas Morning News has a bunch of reporters, and they go out and collect the news stories. They go out and collect them, they bring them back, and they write the stories up, and they put them on a paper, and they print it out, and the next morning it shows up on your doorstep. That's batch processing. So nowadays, how many people have a subscription to a paper, a full-time paper? Yeah, I don't see a single arm. So, and I have friends working at Dallas Morning News, so you're not saying anything bad. You should probably, get one for your kids and show it to them and say, this is how people used to get their news. And so, why don't we do that anymore? Because we don't have to wait 24 hours to read the news. So that's what I'm saying. That's a paradigm shift. We no longer wait until the next morning to find out what happened today. We can find out right now. And so that's the same thing I'm saying is going to happen in the data center. Batch's days are numbered. Okay, that's my prediction. So another way to say that is when you collect a bunch of data and you process it, you learn insights from that. And there's people who've made careers out of that. Business intelligence people. How many BI people in the room? Business intelligence. Okay, how many analytics people? And you keep raising your hand every time. So how many people do like 10 things like Mukesh? Okay. So a lot of us have already made careers out of doing that stuff. And what is the job of a BI analytics person? If you go back a few years, it's looking at historical data so that you can learn from that and make inferences from it. Okay, so now we're migrating out of looking backward looking, and we're trying to make sense out of data as it occurs, as it comes in the door. All right, so another platform. So the tools I'm going to be showing you are all open source tools, and the main one is called Storm. So who knows which company originated Storm? All right, so a lot of the tools that we use in the big data space came out of the Silicon Valley companies. So Hive, which is SQL on Hadoop, came from Facebook. All right, so Kafka, which is the publish subscribe mechanism, came from LinkedIn. Storm was originated by a company. So most people say Twitter, and that's half true. It actually came from a company named Backtype, which was then acquired by Twitter. And so Nathan Mars was the originator of Storm. So Storm is the central point of real-time streaming. We're going to talk about two different types of stream processing, one from Storm and one from Spark. So these tools are the primary tools that do streaming today. And yes, there's Huron. Twitter has moved on to use Huron, and it's a branch, if you will, of Storm. So things continue to evolve. They're not going to stay the same for very long. That's why, if you're like me and you have slides made, you kind of throw your slides away every few months and start over because everything's changed. That's the nature of what we're doing today. So Kafka and Storm, I'm going to show you how to wire up these things. We're going to get a little technical, but don't worry, it's not going to be painful. All right, so what is Storm? So Nathan Mars originated Storm when his company was trying to be acquired by Twitter. He increased the valuation of his company by demonstrating this working. So Twitter ended up using this, and they used it for 10 years approximately. So as you can imagine, Twitter has a lot of events going on at a given time. So again, we're not dealing batch anymore. So when do they shut down Twitter? When does it go down? Do they turn it off at night? Now, if you can't sleep, you wake up middle of the night, you can check your Twitter account, and I can assure you that tweets are being generated. It's an always-on system. It's an always-on system. It never goes to sleep. And so that's another type of differentiation between batch systems. Batch systems, you have that one guy, that DevOps guy, and he goes in and punches the button, right? Because the developers have made it really easy for him. And he punches the button, and then he walks away. And he comes back in 5 hours, and he checks on it and sees if it's done. So what does that mean? It has a start and a finish. So in real-time streaming, we don't have that. Data is always coming in. So Storm, as developed by Nathan Mars for use in Twitter, highly scalable system. It's fault tolerant. It has certain guarantees we'll talk about. It's you can interact with it in a large list of languages, and it is a top-level Apache project. So now, what kind of applications, what kind of companies use Storm? So I already mentioned 3 of them at the beginning. So Hortonworks has a distribution that includes Storm, and the largest Storm cluster in Europe is being run by Spotify. They're running 700 nodes. So a node is a server, like a big, your typical big, data center server that's got 16 cores. That's one node. They have over 700 nodes. So Spotify is running this, doing stream processing, and actually all three of so iTunes is run on Storm and HTTP, and so is Pandora. They switched over earlier this year. So if you're listening to streaming music somewhere in the world, there's events that you are generating coming through Storm or some kind of a real-time streaming process like that. So, and so what it does is you can think about, actually there's many events. When you're listening to Spotify, you or your kids listening to Spotify, what is an event? Okay, an event is like the end of the song. So the end of the song is an event. How many of those events? Spotify has over 40 million users. So songs are ending pretty rapidly, pretty frequently. So that's a lot of events to deal with. And I think that always does it. That skips the next slide. Yeah, all by itself. Okay. So we'll move on to the next slide. So these are some of the different types of processes, including machine learning. So Spark and R are currently being used, as well as some paid products to do machine learning. We'll talk just very briefly about that. But also alerting and notifications. So that's what I'm getting to in Spotify. When a song ends, then something has to happen for you to get that next song, right? So that's an event. A song just ended. So that's the rate at which things have to happen. You're not going to use Spotify for very long if you have to wait, a minute or 2 minutes before the next song starts. So Nathan Mars also talked about the Lambda architecture. So Lambda architecture, and there's another one called Kappa architecture. But Lambda architectures are systems that are built to handle all types of data, whether it's batch, interactive, or streaming real time. So we can go into some of these. We don't have time to go into everything today. But let's talk about, so how does this happen? So when Storm has these components called spouts and bolts. All right, so we're going to get a little technical for a few minutes. A tuple is just a data item. So it's a list of values. And that's commonly what they're referred to. So a stream is just that unbounded sequence of tuples. And so a tuple might be Spotify user 1, 2, 3, 4, 5, 6, 7, just finished listening to song 999, and now it's time to generate another one. So what we have to do is we have to do a recommendation. Right? So these tools are commonly built into systems that do recommendation engines. Who has the most famous, what are some of the most famous recommendation engines in the world? Netflix. Yeah, those are the 2 most famous ones, right? So, these are the tools. So bolts actually do the work, and we'll go into some detail. And I do have a demo, so I actually have 2 demos to show you. But basically, a topology is kind of this here is showing a Storm topology. So we have 2 inputs. We're reading from 2 data sources, and then we're sending that in a series of 1 or more streams and then these bolts actually do the processing. Do we have any? Were there prizes being given out earlier? Deb, do we have any more prizes to give out? Or?
No more prizes.
No more prizes.
Given out earlier.
Okay. Wish we had some more prizes. I'd ask you what a DAG was.
DAG?
Who knows what a DAG is?
That's a piece of poo on a sheet, right?
Okay. I can't refute that.
Data is cyclic.
Yep. So it sounds like a lot of you already know that. So you got to get the Starbucks card down here. All right. So storm architecture. This is in a storm system. There's Nimbus, which is a manager. It kind of keeps track. It's like a job tracker. So there's it's a highly fault tolerant system. So if one of these supervisors crashes, then Nimbus will see that and launch extra tasks. Actually, not if the supervisor crashes, but if the tasks running underneath that supervisor crash. Then it will communicate, and Nimbus will say, okay, you need to restart that task. So it has some kind of fault tolerance built in. Zookeeper is used for state, so all of their state is used there, and that helps us in terms of getting guaranteed once processing, or at least once processing. All right, so in a system, in order to get to utilize a real-time streaming system, we have to get data, right? So we have to get data from somewhere. So I have one of the demos I'm going to show you actually feeds in from Twitter. So it's going to take the Twitter garden hose, not the fire hose, but the garden hose. Where's David? David, I saw him in here earlier. Skip out. So I used to work at BrainSpace, and some people in here are at BrainSpace, and that's what they did is they actually have a product that feeds from Twitter. So you can get a 1%, a 10%, hose, depending on what you're trying to do. So we got to get the data from somewhere. So at Twitter, and for instance, same thing as at LinkedIn. LinkedIn uses Kafka. So Kafka is a massively parallelized, fully durable, persistent message queue. So it's a message queue. There's lots of message queues. Why use Kafka? Well, because the scalability of Kafka is tremendous. So in fact, LinkedIn, there was a blog about 6 weeks ago. Twitter announced that they have joined the 4 Comma Club because they actually processed 1.1 trillion, I don't know how many I got here. They actually processed 1.1 trillion events in a given 24-hour period through Kafka. So they joined the 4 Comma Club. They had a blog post. You can probably still find it. All right, so we're talking, did I do that right? Billion. Okay, yeah. So 1.1 trillion events in a 24-hour period. So that's what we're talking about. These things are massively scalable systems. All right, so we bring the data in. And then we have some choices to make. We can store this. We can store the data in what's called HDFS. That's the Hadoop distributed file system. It's a virtual file system, but you can think of it just like any other Linux or Windows file system. It's just where you write files. You can also store them in NoSQL databases. There's several out there. There's many out there. HBase is our platform, but there's HBase, there's Cassandra. There's even things like MongoDB, which are more really used for document data stores. You can also embed them into search platforms, and you can do in-memory cache. And you can store into traditional RDBMS. So let's break up Kafka. What is Kafka doing? Okay, so these are producers, and those are consumers. Okay, so Kafka, being a message broker, is a place where the messages land. They land there, they get stored to disk, and then consumers, if they want, can subscribe to a given topic. Those are called topics or queues. So you have all these producers. In our case, in the demo, it's going to be Twitter, right? Twitter's generating this data all the time. There's an API that you can connect to Twitter and say, give me events. I have my Twitter credentials. If you're careful, you can snatch mine off the screen in a couple of slides, and you can use my account. But so anyway, producers or whatever the producer, these could be smart devices. These could be your car. Another few months when you buy the connected car. So there's producers and there's consumers. Kafka makes sure the messages are durable and retrievable. So, data is partitioned. That's one of the ways we get parallelism. So at every step when you're going to see in a big data architecture is parallelism. Parallelism is how you achieve these kind of rates. Obviously, that's really one of the key contributions of MapReduce. So, MapReduce is the original paradigm for big data, and it's still in use because even Spark uses it. It just lifts it off of disk and keeps it in memory. So that paradigm of doing distributed computing is still very much alive. and it's how these things are scaled. All right, so this shows, sort of the whole thing. You have multiple brokers. So inside of each broker, we have one or more partitions. One or more topics that are divided into, potentially many partitions, and then we also scale at the broker level, have 2, 3, 4, 10, 20 of those. Okay, so here's kind of the overall system and how data moves through it. You have events coming in, storing in Kafka. Storm is reading those through what's called a Kafka spout, and then optionally writing to one of the message stores, either HBase, Hive. Yarn is a data operating system that's running. All the jobs get submitted through Yarn. Okay, we're gonna get through. We're gonna skip some of these slides. Not even sure how long I have today, but let's go ahead and show you something working. All right. So the first demo I'm going to show you is actually not running on my laptop, but it's running in our cloud. Okay, so this is the Hortonworks Embari tool, which is the single pane of glass. It's a management and monitoring console. All of these things over here are services. The green check mark says they're up and running. So you see that we have a long list of services that are running available to us. Now, what I'm going to do is, for this demo, we're actually going to walk through we're going to simulate a trucking scenario. So let me go ahead and kick this off. And then let me switch over. I'm going to introduce this demo here and tell you what's going on. So let me switch to this. All right, so here's a scenario. So we have a trucking fleet out there, right? So that could be like FedEx, UPS, it could be Amazon's delivery, or Walmart, or AT&T, Fios, Verizon, Fios, whatever. So, lots of companies have, fleets of vehicles for one reason or another. Even AT&T, they told me that they have 8,700 trucks. He was like, who knew? It's like, but those guys got to get to your house somehow, right? So anyway, this is the scenario that I'm about to show you, and I'm going to show it to you live. This is the architecture, which we've pretty much talked about. But so what's happening is we're simulating these events, but we're imagining that there's trucks out there, like hundreds and dozens of trucks out there generating this data, and the data they're generating is about two kind of classes of events. One is just a normal event. So, got in the car, started it up, and started driving. That's an event. And a negative or dangerous event is I'm exceeding the speed limit. So who thinks that when they're speeding nowadays that nobody knows that they're speeding if they don't see a cop? If you're in a rental car, they probably already know you're speeding. They can probably write you a ticket when you get back and turn it in. Anyway, these events are coming into the system, and then we're trying to divide them into dangerous events or normal events. All right, so we're going to look at these events, and I'm going to show it to you in a minute. But we're trying to figure out, as a company, if we can be sort of predictive and figure out how to eliminate these dangerous drivers. Maybe not the dangerous drivers, because so drivers aren't necessarily dangerous, but they make dangerous decisions, maybe. The events themselves are what the problem is. So if they have a wreck and somebody gets injured and we get sued, if they hurt themselves, if we have to fix the truck, there's lots of bad things that can happen, right? So nobody wants to have accidents. So speeding, rapid lane changes, those are the kinds of things that right now your insurance company wants to put a sensor in your car so that they know how good of a driver you are. You go back even just 10 years, how did they assess whether you were a risk? They looked at your age, your gender, and your address. That's pretty much all they knew about you. They said if you're under 25 and you're male, you're dangerous. So we're going to charge you accordingly. So that was sometimes true, but a lot of times it wasn't true. And so now they want to collect information on your driving habits. We can figure out if you're a safe driver. We just got to put the device in your car. We'll figure it out. So we have all these events. So maybe we find out certain things, like certain drivers are more dangerous than others. That's a theory at this point. All right, so here's what's, we have this simulator out here that's generating these events for us. We have the tooling that I showed you. And now, we're going to show you that, so this is running live. This is not video. So right now on our cloud servers, we are using Storm and Kafka to draw these dots. And so these are drivers that are driving on certain routes in, looks like the Midwest. I see Kansas City. And as we collect data, we're going to post up here we're going to collect and sort that data by driver. So one of the things we're going to do is we're going to try to find out if we see negative events over and over for a given driver, then we're going to try to flag that. So we're trying to collect that data. If I scroll down here, you'll see this is the type of data that's being collected. So we have driver name, we have the route, we have IDs, we have a trucking ID, and a truck ID and driver ID. And we also have lat long. That's important too, right? So we need to know where these events are occurring. So nowadays everybody's geocoded everything, right? So we know where these things are happening. Now, if we have a particular driver we're interested in, we can find out. Okay, so over the last month or year that we've been tracking, this driver's had 723 violations. So that's not like a ticket. That means he's changed lanes too rapidly, or he's exceeding the speed limit. Those are sort of quasi violations, right? But they're negative. They're things that we don't want to have happen. All right. So this is. Right, so this is an example of how to assimilate and make use of this data. So another tool we have at our disposal is we can use Spark to look at these events. So this is an example of some of those events. We have the event type, we have the lat long out there, we have a driver ID and a truck ID, I think. Must be static electricity is hitting my computer. Okay, so anyway, so consider this a real live scenario for using this data. So let's jump back to here. So what kind of things can we learn? We can also analyze maybe if certain routes are more dangerous than others. We could learn that from analyzing this data. We can start to group them by location, by lat long, and try to figure out if some locations present problems. So these are the types of things that we can do. We can also look at the driver himself. Let's make this a little bit bigger here. We can also look at the driver himself and figure out, okay, well, maybe if we enrich the data. Okay, so that's a tool that a lot of people have to do now. Is in order to you have a data set, it's somewhat useful, but you gain a lot more power when you start enriching that data. So you saw that the trucking data, the event data wasn't very much, right? But what if we start to enrich that and we start to correlate that with the historical patterns of the driver himself, he or she? So is that driver certified? So we have a certification program. Maybe it's the uncertified drivers who are causing the most incidents. Now, that would make sense, right? But maybe, we'd have to test that theory. Maybe it's another assumption that maybe it's as drivers drive longer, they get fatigued, and so maybe the number of hours that they're driven or the number of miles they're driven is really the key predictor. So as a company, we might want to figure out, let's plot these events by certain ways. So if we plot them by hours driven, that's 92 hours in 1 week. Okay, so that's, if we come down here and we see drivers driving 45 hours, the ratio of red events is not as high. If we go out here to 92, now that's a lot of driving. I mean, that's, how many of you work, 92 hours this week? I mean, generally we say we work about 80, right? So, and so we tell our employees 60 hours this week. So if you're on the road for that many hours, maybe the number of negative incidents goes up and that seems like a very reasonable thing, reasonable assumption. So there's a lot of ways to slice and dice this. Maybe certain routes are more dangerous, etc. So these are some of the tools that we have at our disposal and we'll come back to that. But let's, all right, so there's a lot of talk about complex event processing or simple event processing, and at some point we have to hook up analytics because while it's very useful to have a real-time dashboard, then we need those business intelligence people, the analytics people to come in and actually hook up some analytics to that. Those real-time key KPIs, key performance indications, those are useful for reacting to things as they occur. But we also want to hook up some kind of predictive analytics to it. So what we're doing is we're using the same tools. We're going to extend the power of that, and we're going to